Well, I'm really glad to see such a good turnout given the party yesterday. Did everyone have a good time? There's not a big round of applause or cheer, which is like, well, I completely understand that. You're probably sitting next to somebody who's got a bit of a headache right now. For those of you who actually are feeling pretty good, I hope you enjoy the talk today. For those of you who are feeling a bit hungover, if you are going to fall asleep during the talk, try and keep the snoring down. That'd be great. Thank you for coming along. We're going to be talking about microservice security and a bit more as well. My name's Sam Newman. I wrote a book. Out of interest, has anyone here read my book? A few people have. Excellent. Thank you. Okay, well, that's good. I am working on a second edition, but that'll be out sort of this time next year. I now also run my own company doing sort of training, consulting, and advisory work. If you want to know more about what I do, you can find my details out on the internet. That's the end of the plugs. I've been interested in security for a while now. I consider myself to be a conscious incompetent. That means I know that I don't know much. I'm trying to educate myself. And it's sort of hard to avoid now the conversation and discussion about security and privacy of data. We live in a world where we have massive data breaches, it seems, on a weekly, if not monthly basis. Now even our actual chipsets and our CPUs now need to be patched. And so the threat of some sort of malicious party taking advantage of some kind of security defect is ever present and all the more pressing. And I think in any case, there's been a much wider awareness of security and privacy issues in the post-Snowden era. And so I think as many of you are technologists now being faced with the task of thinking a little bit more about security. But I think as though many advances have happened in our industry in terms of thinking more holistically about the process of software delivery, we think now sort of in terms of the holistic, okay, I'm going to design the software, we're going to build that software and ship it. After testing it, obviously, we're definitely going to test it. And then hopefully we're going to learn from this, thinking of these sort of lean iterative cycles of sort of build, ship, deploy, learn, and those loops. And we've brought a lot of new disciplines into the art of software delivery. We used to say, well, I don't need to write tests because I know my code works. So we had another set of people separate from us writing the tests. We sort of still have that same approach towards security. Security is somehow that something's off to one side, and it's such a dark art. It's too specialist. We have to have a lot of experience to be doing security. You have to bring in some special experts, and they look differently to you, and they wear different outfits. And you can afford to bring them in maybe once a year. We'll do a pen test. That'll be fine. And I think the reality is we are with security where we were with testing, say, 15 years ago, which is we're in a state where a lot of the industry realizes it's important, but at the same time, as developers, we kind of don't know what our role is. Do we have to know everything there is to know about application security? Do we need to know just enough, which I think is where we are with testing? And I think with security, there's certainly a baseline level of awareness I think most developers need to have. And so part of what I'm going to be sharing with you today is just enough security that I think you need to know as an application developer in the context of microservices. Because microservices create some kind of interesting challenges. Now, I actually have been a strong proponent of microservice architectures in the realm of security, but it's very much a double-edged sword. With a monolithic system, and we talk about a monolith as a unit of deployment, but we also talk about monolith in terms of how the data is stored, we sort of have this issue that if that application is breached, if people gain access to that information, to that data, everything is right there. You only need to breach the application once to have breached the entire application suite. And this is sort of a problem, right? Because all of your information is in that one place. Now, to one level, it's nice. It's a simpler world. We understand where things are. And believe it or not, I have worked with many microservice teams whose most pressing problem is we don't know what we've got or where it's running. It's quite difficult to protect a system when you don't know what it is or where it is. With a monolithic system, you do have this very straightforward characteristic. It is there. It is all I have. But by the same token, all of your data and all of your processing is in that one place. So to an extent, it's sort of a bit more vulnerable. With a microservice architecture, if one of my services gets breached, we only have one application that's been breached. We only have one set of data, hopefully, which is being compromised. This is assuming that you're adopting one of the cardinal rules of microservice architectures and encapsulating your data and hiding your data behind well-defined service interfaces. This opens up the possibility of us protecting some services and applying more oversight than in other parts of our system. If you're operating, for example, in an environment where you have to worry about things like the GDPR, this should theoretically allow you to limit how much of your application needs to get the same sort of regulatory oversight as other parts of your application. Your focus is going to be on where is my personally identifiable information? What is the ingress and egress from that service? And hopefully, you can focus your time, energy, and attention on that, which might make adopting some of the GDPR stuff more beneficial. You also, with a microservice architecture, have this property of being able to defend in depth. If you've ever seen, well, you've seen a castle. We're in Vilnius. There's a big castle on the hill, right? If you've ever seen big castles around the world, you see castles typically deploy defense in depth. They'll have like they'll be on a hill, then they'll have a wall around the hill, and then they think, well, people can climb up the hill and then climb over the wall. Okay, we'll put a moat around the wall, but then people get boats. Okay, we'll put a wall, then the moat, then a wall, then a hill, then a big tower, and it just keeps going and going and going, actually, and you saw this development all across Europe until the age of gunpowder. But when it comes to sort of our microservice architectures, we do something similar. We have the ability to think about defense in depth that can apply in terms of things like network perimeters. I was discussing yesterday with some people, even when it comes to, say, using the cloud, something as simple as having different services running out of different accounts can provide some useful logical grouping and protection mechanisms. So that's all the good side, isn't it? I've got defense in depth. We can focus on where our most sensitive data is. That sounds great. But the flip side with microservice architectures is that all this information that used to flow within a single process system, that used to flow just inside a single running operating system, is now flowing over networks. And that's kind of interesting because the kinds of attacks that would be able to get hold of information running in a single process system are somewhat sophisticated and aren't as many. But there's loads of different ways in which I can get hold of data flowing between services and also potentially manipulate it. We also have many more services that need to now be protected, maintained, patched, and everything else. I sort of have a belief that if you're quite savvy around security issues, that you could probably build a more secure system with a microservice architecture. I think most certainly you could. I think if you're not as aware of sort of general application security principles and maybe sort of adopt a will apply security later type mentality, then I actually think a microservice architecture could be downright dangerous for you. And we're going to be exploring this throughout the rest of the talk. I do want to get some basics out of the way first, though, because there are some basic fundamental aspects of security that I always try and sprinkle in these talks, because basically I use the big meaty hook of microservices to get you in the door, and then I try and educate you about some things that are applicable to all software delivery. So I'm going to go through a few of those things now. So hands up here, who here thinks they're really good at assessing risks? Now, see, what's actually happened here is you know that I'm going to get some of you to put your hands up and then show how you don't know how to assess risk. You're all being very smart and savvy by not putting your hands up. Also, some of you probably went to the party last night thinking, I won't overindulge. I know there's a risk that I will, but I'm not going to do that, am I? And now you're thinking about that and you're thinking, oh, I did drink too much, didn't I? So you know you're not very good at assessing risks. This is good. But a lot of people overemphasize certain things. We think we actually can, and I too often see people talk to me about how they're going to defend their systems, and they start talking about the big, shiny, big-ticket items without dealing with the basics. There's a really good report from Verizon that they put out every year. This is a data breach investigations report. This mostly looks at Verizon's customers in North America. So it's a bit of a North American skew, but there's a lot of intricate detail there. And they've been doing this report for a number of years now, so they've got some interesting trends. This is actually taken from the 2017 report. The 2018 report is out, but I haven't yet updated it. And they show that when you look at breaches and you look at the mechanisms used by attackers as part of those breaches, by far, the most common mechanism used as part of data breaches is basically stolen or weak credentials. It is passwords. It's sort of a very simple, basic thing. There is some great information out there about how to use passwords. Troy Hunt's got this nice write-up of how we should think about password management, which in turn is actually based on advice from NIST in the US and the UK Cyber Security Research Centre, which is normally dry government advisory bodies, and in IT, they seem to often be kind of about 10 years off the pace. But actually, there is some great advice in here. So some of the tips in this report are things like, well, longer is stronger. I went to sign up recently for an Office 365 login. Do not ask why I needed Office 365. Let's just say buying a house shouldn't involve you having to have an Office 365 membership, but apparently it does. When I went to sign up for this account, I was typing in my password. The password was limited to 12 characters in length. Now, this is interesting because if you know anything about how passwords are actually stored, they should be actually hashed into quite a long hash that is then stored in the database. So by making a password being very short, you have a problem. You need to create entropy with that password, which then leads you, if you say you can only use 12 characters, you have to get entropy from variation of the individual characters. And so you basically end up with these complex character composition rules. Which get very confusing, and as a result, people pick passwords which are easy to crack because they're in dictionaries where common passwords like capital P, @ 55W 0RD is a very commonly used password that will pass most character composition rules and is in every dictionary used by crackers all over the world. And so you get very complicated schemes that are really hard to understand and cause you to come out with some very bizarre, easily guessable things, or ultimately write it down on a post-it note on your laptop. So this is stupid. If you allow people to type in longer passwords, they can use more natural language, and you can still get the entropy you want. Other issues, embrace password managers. So hands up if you use a password manager for your personal passwords. Okay, it's about half the room. Now hands up if you use a password manager at your place of work. So that's the same number. That's good. That's a trend I've seen change over the last 2 years. It used to be that people would use them for their personal passwords, but not their work passwords. For those of you without your hands up to either question, get a password manager. They will allow you to generate unique passwords for each login, and some of the more sophisticated ones will even pick up breached passwords. This is another interesting one. Do not mandate password changes. This again seems odd. One of the concerns with passwords is, well, if you use the same password for a long period of time, someone might gain access to it. You're increasing the chance that someone's going to hack into your system. Turns out that actually constantly mandating password changes just trains people for phishing attacks. Because what happens, you wake up in the morning, you go to work, I've got to change my password, current password. Okay, type it in, enter. New password, enter. Every 3 months, I've got to change my password. So you're just used to boxes popping up saying, what is your current password? Please give us your current password. And you think, oh, yes, I'll put it in, it's fine. And before you know it, you've been phished, right? And so this is actually, do not mandate password changes. And instead, what you should be doing is blocking previously breached passwords. Troy Hunt's tool, Have I Been Pwned, is now looking at passwords found in data breaches. Smart companies are now emailing their customers to say, it looks like you're using the same username and password combination for our system that was involved in this breach over here. Our systems haven't been attacked, but we're going to require you to change your password. That is smart, right? That's very, very smart. Now, you also need to keep type control over those credentials. This is why having password managers is good, because everybody can have their own set of passwords. Has anyone here heard of a company called Codespaces? So I'm looking around. Has anyone got a hands up? Well, the reason no one's heard of Codespaces, and that's because they do not exist anymore. So Codespaces was a website, a system, a SaaS-based company that provided, and this is ironic, secure source code hosting. What happened was the root credentials for their Amazon account were basically breached in some way, so we don't know if it was a malicious ex-employee or just somebody who found these root API keys, checked in on the internet somewhere, but they basically used these API keys to delete all of the Amazon resources on their account. So their entire production systems were taken down very, very quickly. And you're saying, well, that's okay, Sam, because they obviously had backups. Yeah, they had backups. The backups were in the same Amazon account. So when you talk about off-site backup, that means different things on the cloud. But that's okay, you say, Sam, because, Sam, obviously they had their source code, so they could rebuild the site from scratch. You can see where this is going, can't you? The source code was in the Amazon account. So, limiting the scope of credentials is also quite key, is also quite important. So doing things like time-limited generation of things like Amazon API keys for the things that are really, really important, and drastically limiting the scope is also important. There is no cost to having multiple Amazon accounts. For example, I've been doing Amazon training courses since 2009, and one of the first pieces of advice we give is have a separate account for dev and test, and maybe even test and prod. And with teams I work with now do microservice architectures, I definitely want per team accounts. So if one team account is breached, you've limited the impact of that system. There are actually tools out there that will check for logged in, for sort of checked in API keys and the like. We know that Amazon and Microsoft actually scan GitHub looking for things that look like there could be API credentials. I've also used GitRob for basically scanning internal Git repos, looking for things that look like the pattern of an AWS API key, and that's very useful. Although on the cloud providers, you should all, in a corporate setting, be using some kind of time-limited credential generation. Something like AD Federation on AWS, for example, is a great idea. So for some kinds of credentials, we want them rotated frequently. Things like the API keys that we might use between machines, things like the Amazon API keys, where we want to get hold of a credential for a very short period of time. This is typically being used by a computer talking to another computer. By rotating those credentials frequently, we limit the risk where even if we did accidentally check in the private and public API key pair for our Amazon account, if those credentials are no longer valid, then it doesn't really matter that much. So this idea of revocation of some credentials makes a lot of sense. Think, Amazon API keys, service API keys, also things like database credentials for your services. And that's difficult enough to do when you've got a monolithic system. But when you have a microservice system, this can be really difficult because you've got a lot more stuff. Think in this situation here and all the services I've got all the shared secrets that I might be using. If I'm doing HMAC for service-to-service communication, for example, then I've got the private keys I've got to worry about for validating the request hashes. I might also have, and that's now, if I change a shared secret across these machines, I've got to roll that change out to these 6 logical services. These 6 logical services can, of course, be scaled out over multiple other services, instances themselves. So we need to find ways to automate rolling out and revoking and changing credentials for microservice systems. We start thinking about a single database as well. Of course, I need to talk to my database. So I've got all my, and these are probably in a file somewhere. So if someone gains access to that data, that text, they can gain access directly to my database. And so, we don't like leaving these credentials out in the open. I know in the early days of Docker and containerization, there was a lot of challenges in terms of how you got secrets into machines. For example, you could, do you specify these things as environment variables? Well, who has visibility of environment variables? If I put them on the disk, how do I ensure that other containers on that same machine can't gain access to my file systems and things? These things are actually fairly well documented now, but even so, it would be very nice if we had some way of changing these credentials on a regular basis. Because otherwise, if someone gets hold of them, something bad could happen. This is where things like secret stores are incredibly useful, and especially for a microservice environment. Now, I am a big fan of Vault. HashiCorp have done some awesome stuff, but the most awesomest of the stuff they've done is Vault, which is a really interesting system. If you are on a public cloud provider, most of the public cloud, well, certainly I know that AWS and Azure both provide some form of a secret-based system, which you might want to get away with. It's good enough for simple cases. So you've certainly got things like AWS Key Management Services and Parameter Store, which do a pretty good job at this stuff, actually. Vault is kind of much more interesting. It kind of works in a very simple way. You go to Vault and say, I would like the login and password for my database. And Vault can do really clever things, like it can actually talk to your database and generate you a brand new username and password just for you, and it will give you that username and password. It will also make sure that those credentials will change on a frequent basis and reissue you those username and passwords when applicable. And so Vault has these backends that can talk to various different database providers, for example. You can also use it for doing exactly the same thing with the public cloud providers as well. And this allows programmatically for you to request generation of credentials from your application itself, which is super smart. But you can also, I know quite a few teams that just put very simple front ends on these things for human beings to use Vault to generate these things. The way Vault works is really, really interesting. I'm not going to go into it in detail. I do have a whole 3-hour thing on microservice security over at O'Reilly's Safari bookshelf. You can watch me. It's like this, but in 5-minute chunks that you can watch during your build times. And I go into a lot more detail on how Vault works. But there's loads of great material out there. One of Vault's special tricks is it works really well with a tool called Vault Console Template. And so Console Template is a very simple tool, and what it does is it takes text files and basically updates those text files based on values held either in Console or in Vault. So in this situation here, I've got my username and password credentials for my service in some sort of template form. When Vault decides that those credentials need to change, it can actually make use of Console Template, basically pulls that new data and updates my local text file. And so now suddenly I've got an application that knows nothing about Vault. It just reads its properties, its configuration values from a text file. I change them in Vault. I change them in Console. That text file dynamically updates, right? Fully automated. So that's a fantastic way of managing credentials in a distributed environment. And again, could well be useful for a single monolithic system as well. Coming back to other types of common breakages and common types of security problems that occur. This is a 2016 report from Forbes BMC, which showed that 44% of all security breaches occur after problems are already identified, but patches have not been applied, where protections have not been applied. So basically, they find a problem, do nothing about it, and then the problem they found ends up being the reason why the site or the system or the data was breached. A great example of this would be something like Equifax. Now, how many people here have heard of Equifax? Well, I know the Americans in the room have heard of Equifax because there's a good chance they lost your data. Well, they didn't lose it. They just don't know where it went. It's a different thing. So Equifax, for those of you who don't know, are one of the main credit checking systems out there, the main credit checking sites. So to do credit checking, they actually have to have a lot of information about you, things like in the US, your social security number, your bank account details, potentially how much money you make, where you live. And unfortunately, this site was hacked and all this data was stolen. There was actually a bug in their software, which was caused by a vulnerability in struts. You go and look up what the vulnerability was on the CVE database, and you see it has a thing, it's called the CVSS severity score. And it has a score of 10, 10.0. That's how bad this defect was. Now, that is not a scale out of 100, and nor is 10 at the good end of that scale. 10 is the worst possible end of that scale you can have. It's not a thing to be proud of. Yeah, we got a 10. The 10 is bad. 10 is as bad as it possibly gets. This particular bug in the struts library was found early March. Oh, it was actually not found. It was found before that. It was reported in early March at the same time as the struts developers put out patches to fix this defect. It's a common thing with very vulnerable, or with very serious defects like this, is for the researchers to collaborate with the people who are creating the software themselves to make sure that the patch is available at the same time it's reported. Which is so serious that you can't leave a gap between those two things. So it was patched on the 7th of March, the same day the bug was reported. So this was very widely communicated because it was a serious issue, and struts is still quite widely used in a lot of places. So Equifax, of course, needless to say, did not apply the patch. What we know in terms of how the data was breached, that sometime between May and July, their data was breached. Okay, we're not quite sure when. Equifax themselves say they spotted it on the 29th of July. They reported it to the public on September the 7th. Can you see the little problem there? Little gap there? Just a little gap. What's a little gap of 6 weeks between friends when they've lost all of your information? The US does not have mandatory data breach reporting laws. That is something that is in the GDPR. I will just leave it at that. There was also a small matter of a bunch of Equifax executives selling stock between those two dates, which I'm sure is completely coincidental, and I'm sure they're definitely not being investigated by the SEC, even though they are being investigated by the SEC. So, bit of a gap there. So we know that by the time they found out about the breach, there'd been anywhere from a 2 to a 4 month window between the patch being available and this sort of vulnerability being used to beat the site, to crack into the site, right? So a 2 to 4 month window. So if they'd applied the patch in 7 weeks after the patch was available, they probably would have been absolutely fine and no one would have noticed this whatsoever. So a 2 to 4 month window is what they were dealing with here. So hands up if you know that you patch all of your systems every 2 to 4 months. Put your hands up. We've got some hands up. We've got some hands up. Okay. The problem with the microservice architecture, especially your modern microservice architecture, by which time I mean it's this sort of massively containerized and virtualized platform, you have kind of an interesting nesting problem, right? You've got things and things and things inside other things inside other things. It makes it very hard for us to now reason about what are all the things involved in our system. And so when I ask a question like how many of you know all of your system has been patched, well, let's dive a bit deeper. Let's look at a modern microservice deployment stack. We start with the underlying hardware, because even though it may be serverless, there's still some silicon involved somewhere. On top of that, we have our operating system. On top of our operating system, we have our hypervisor. The hypervisor vises hyperly. And then on top of the hypervisor, we've got our virtual machine operating system, which is a full stack operating system complete with its own kernel. On top of that, we obviously have Docker or some other kind of container engine. On top of the Docker container engine, we have the container operating system. And on top of the container operating system, you have your application. And this is simplified a bit. I haven't talked about Kubernetes. And all of these things need patching, every single layer. Spectre and Heartbleed, we had to apply patches to our hardware. So how many people now are still confident that they apply patches at every single layer in their deployment stack in a 2 to 4 month window? And no. We've got 2 people, and I bet they're not running microservices, and they're probably running on paired tin, right? So yeah, this is the problem. Now, you might be, the issue is visibility. Do you know? For those of you at Russ's keynote yesterday, he said, how many of you know your system is up right now? And then said, how many of you know your system is up right now because no customers have told you it's down? Right, this is the same thing. You hope. Hope is not a strategy. So probably this is going to cause some issues. So what can you do about this in a microservice environment? Well, if you're looking at, say, moving over to a public cloud, and maybe just adopting that public cloud at the level of infrastructure as a service, so using basically managed virtual machines, you can be reasonably confident that at least this part of your stack is going to be dealt with by that public cloud provider. Amazon, Google, and Microsoft all had applied, for example, patches to Spectre and Meltdown within a week of them being made available, which we realized because all of our machines suddenly were 30% slower. So this happened. Now, obviously, if you're going for a more highly abstracted cloud-based service, you can, for example, you're using something like ECS or EKS or one of the other managed container orchestration platforms, you're offloading more stuff to the cloud provider. So hopefully, they're going to do a better job than you are of managing patching at this level. And of course, that still leaves the stuff on top. If you're deploying your own container workloads onto a cloud-based platform, the operating system inside that container is your responsibility, as is and as are the third-party library dependencies that you may have, which are sort of sitting up there as well. Function as a service, you have even less control, and so you're just going to be worrying about your functions. But even then, there's nothing to stop me running struts in a Java function on Lambda on Azure, right? So I still have to worry about that sort of stuff. Now, there are container scanning toolkits out there that can actually look at vulnerabilities in your container images. And this is really quite useful because one of the problems of microservice architecture when it comes to these sorts of things is once you create say, a container-based microservice and it's running, you don't go and patch it. You see it as being immutable. So what happens when it's Patch Tuesday and your service has been running for a month? Do you shut it down and repatch it and redeploy it? Most people don't. They just leave these things running. So if you haven't touched that service for 6 months, there's a 6-month window of unpatched stuff. So actually having tools that can look at the images you've got, and Docker image layering opens up some interesting possibilities in terms of how you can do image vulnerability scanning. Could be a useful thing. We've got open source tools now, well, we have for a while now. Claire buckles a bit after a while, but there are also commercial tools out there that are well worth looking at. I take a look at Aquasec, which is well worth looking at. But we also have our application developer dependencies. These are things which are squarely under your control. Think about all the third-party libraries you're linking to. And here we've got great tools like Snyk. So Snyk will look at your source code repos, it will look at, say, your manifest, your dependencies, and they have a massive CVE database on the back end, and when they spot vulnerabilities, they say, oh, you've got YAML parser 1.1, there's a critical vulnerability, you need to upgrade to 1.2. You can actually integrate this in your build, so your builds will fail if you're depending on out-of-date dependencies. It even goes a bit further, it will send you a nice pull request and say things like, here's actually the update for you. So it will say, not only do you need to upgrade to version 2.0 of the YAML parser library, it will send you the change, and all you have to do is click on the OK button. That's quite slick, and again, is very reasonably priced, so definitely worth looking at. Now, a lot of this stuff I've shared with you is basics. Some of these things get hard in a microservice environment, but these are, and I said earlier, many of us are not good at assessing risks. And I think that's also why it can be important for you to do some kind of threat modeling exercise. If you've not done something like this before, it does seem a little bit daunting, but even running these, and it's always good to get an expert in for these things if you can, but even if you can't, just working through one of these threat modeling exercises definitely has value. So Microsoft have a great website with a secure developer lifecycle. There's loads of information here about things like stride and dread-based threat modeling, taking you through things like attack trees. And going through an exercise like this to think clearly about where are we actually vulnerable, what are the weak spots in our system, is a great way of helping you better assess the risks that you might have, rather than focusing on some of the shiny stuff. We're going to get to the shiny stuff in a moment, all right? And let's do that now. Actually, let's take a look at a modern microservice architecture. Those of you who might know my talks previously will know I often use a fake domain of a company selling CDs online. You can tell how long I've been using that example for, because we are selling CDs online. I mean, we might as well be selling 8-track. Vinyl is also a growing business. So here we are. We've got our modern music company with our user information stored in the user service. We've got our front end, which is served up by a music web shop. We're not messing around with any of this single-page app nonsense. This is a website for web people. We have a catalog where our information is stored about the artists, the albums, and everything else. And we have just been dragged kicking and screaming into the world of streaming, because we've seen how much money Spotify are making, we think. We've got that scaling agile at Spotify paper, and we think that's all we need to worry about, so that's going to be fine. So these are our services that talk to each other, sitting within our perimeter. We've also got upstream clients, we've got mobile and web clients, and we've got a downstream party where we send all of our royalty payment information, so communicating with a trusted third party over the internets. So one of the things I said at the beginning was we've got to think about the information that flows between services. This information that used to run and exist within our single process system is now flowing openly between services. So what is it we're actually worried about in this situation? There's kind of 4 key concerns. The first thing is, can a malicious party see the data that is flowing between trusted parties? Can we see the data? The second thing is, can that data be manipulated in some way? So I see that Sam is being paid £100. Wouldn't it be a lot better if, in fact, Sam was paid £200? I think I can agree that that is definitely what we want. I'm not sure that's what you wanted, so we need to be careful that the data isn't actually being changed. We also want to make sure we restrict access to the endpoints. You can lock your database down as much as you like, but if the service that has authorized access to that database is running on a completely open port, which doesn't do any client-based authentication, then I can just go and use curl to extract all of your data from your database via your lovely REST-based microservice. So we need to restrict access to those endpoints as well. And we also want to make sure that the endpoints themselves are not impersonated. which is a kind of a nasty malicious attack. I've not seen many examples of this happen, but very early there was like a great theoretical attack against Kubernetes where you could bring up your own Kubernetes node and have it join an existing cluster. And so then when workloads got sent to the machine where your node was running, you ran as a privileged container and could hoover up all the information on that machine, which was really clever. I don't think it ever actually happened, and that's been locked down now. So these are sort of our 4 main concerns. And so we're going to take a look at some sort of common stuff to help us here. And obviously, the starting point for many people is just because you're probably using some sort of HTTP transport if you're making use of, say, synchronous communication, is just saying we're going to do HTTPS everywhere. So by this, we mean HTTP and TLS. So HTTP and TLS gives us server guarantees. So we know the server we're talking to is actually the server it claims to be, assuming you're validating your certificates. It's remarkable how many environments I've worked with clients where they're using HTTPS but are not actually validating certificates, which basically is pointless. It also gives some guarantees that the payload itself has not been manipulated, defends us against things like man-in-the-middle attacks. Unless we go that extra mile, does nothing about the client. So anybody could still be accessing that. So we haven't really restricted access to that endpoint. And historically, people would complain that certificate management was painful. I think this is a rubbish argument now. I don't say that lightly, but really is. This is a very poor argument now. The other poor argument is, oh, HTTPS adds a 20% overhead to all traffic. That was a stat generated about 20 years ago, which hasn't been applicable for a very long time, so don't worry about that. Certificate management used to be painful, it's not anymore. We've seen a whole load of different platforms out there that provide automated issuing of certificates. So Let's Encrypt, for example, backed by the Linux Foundation. Everyone went crazy when Let's Encrypt came out. They said, look, it's going to let me generate a free certificate. It was never the money. Was the $25 fee to Thwaite the thing that stopped you implementing HTTPS on your public-facing website? It was not $25. It was the fact that the process was manual and painful, and now it's fully automated. This is the killer. You want some automated mechanism for creating, installing, and reissuing certificates. Again, here, you've got things like Let's Encrypt available to all. All of the public cloud providers make this fully automated as well. There is zero excuse for not doing this stuff nowadays. So yeah, you've got things like Certificate Manager, and Azure has a similar service as well. And we'll even let you install those things and terminate those things on the API gateways that they provide too. So just looking at HTTP and TLS, and see how it stacks up. So great, we've stopped observation of data. We've stopped manipulation of data. We haven't necessarily restricted access to the endpoints, but we have stopped impersonation of the endpoints. And so that's good. And so probably as a default choice, I will just say, I'm just going to use it everywhere because it's not that hard to do, and obviously over anything that goes over the public internet. We can do better, and this is where we move to something like mutual TLS. With mutual TLS, we basically install a certificate on the client so that we also have client-based identification. So now I've got, this is much better, much better. So now we make sure it's only allowed clients are able to communicate with our server-based endpoints. Now again, historically, certificate management here was very painful, but again, if you're on the public cloud, this is a much easier process. Azure, for example, makes it very, very easy for you to install client-side certificates using the API gateway and manage those and reissue those. So the argument about this being hard on a public cloud environment doesn't really stack up. Can be a bit harder if you're in an on-premise situation because historically the tooling around this has not been great. Like you had Netflix Lemur system, which never really caught on. But we'll come back to this a bit later on and touch on something that might help you in on-premise situations. So mutual TLS is pretty good, right? It stops data being observed, it stops data being manipulated, it restricts access to endpoints, and it also stops us impersonating endpoints. So mutual TLS is a pretty good situation here. Now, I would say even if I had to manage my client-side certificates in a manual fashion, I'd still consider using them in this sort of architecture. For example, if I'm thinking about communicating with trusted external parties running over the public internet, I might use something like a Bastion server to install my certificates manually on my perimeter to manage the communication between those two services. So even if I was doing that manually, now if it has automated it, I'd be using it sort of everywhere throughout my perimeter. And this seems to be a bit of a baseline now. 4 years ago, most people were doing nothing inside their perimeter. Nowadays, this tends to be table stakes for people building HTTP-based service architectures. Now, other protocols. What about, oh, I'm using something else. I'm using some sort of asynchronous communication protocol via a message broker. I'm using, Rabbit. I'm using Kafka. Well, again, your broker has your back on this one. What you're going to need to do is look at what message broker technology you're using and understand what they provide. But certainly, both Kafka and Rabbit provide TLS equivalent protections. I think in the case of Rabbit, you have to just install some Erlang OLTP modules. But apart from that, it's a pretty easy thing to do. And there is lots of documentation out there for how that stuff works as well. Now, so far, what we've basically handled is transport-based authentication, but we haven't really dealt with the whole picture. So what we've basically dealt with is how computers talk to other computers. There are other techniques out there that we can use, but basically this is computer A saying to computer B, hello, I am computer A, and computer B going, oh, yes, you are. Hello, computer A. I'm going to let you talk to me. And this is what we've dealt with so far. We've got server-side identity dealt with. We've got client-side identity dealt with to an extent. We've basically solved service-to-service authentication to an extent. The problem, of course, is that it's not all computers talking to computers. Computers can be trusted. Sometimes. What we're actually what's even more problematic are human beings. Human beings cause issues. Human beings who use our software. With human beings using our software, we have the issue. So when they come along and they want to log into our site, we have to validate and make sure they are who they say they are. You're probably going to use some kind of authentication gateway. That's where your sort of login redirection flow is going to be done. And so what's going to happen is you're going to make sure that only authorized users are actually going to be able to make requests that go past your auth gateway. So you're going to make sure they're logged in as you get through. So you'll get bounced off. Some people use libraries in their perimeter services. Most people I meet have some kind of gateway appliance that handles this for you. So only Bob, if he's logged in, will actually be able to get through those requests. And that's sort of nice, but we have a different problem because there's authentication, which is Bob is who he says he is. And then there's also authorization, which is the other problem of what is Bob actually allowed to do. So we take a very simple situation. So Bob comes along and says, hi, I'm Bob. Hi, I'm Bob. And the auth gateway says, really? Are you really Bob? Are you sure you're Bob? And up pops a little login. You type your details in and go, yes, I am Bob. And so what will get done, I'll get like a little token issued that represents my logged in state, probably with a cookie with an expiry. And then, and only then, when requests come with that token, am I allowed to then talk to this service. So that's the authentication part of this. Let's look at the authorization part of this, or rather the lack thereof. So in this situation, Bob is going to look at his profile. Bob clicks on his little profile icon, and it takes him to this URI. And so he makes that request to the auth gateway. That request goes to the music web shop. So the music web shop is busy rendering this HTML page, replete with all Bob's information, showing just how many One Direction and Justin Bieber CDs that he has purchased over the time. And the music web shop is gathering that information, but then it realizes, well, actually, there's a bunch of things that I need to put on the user profile page that I don't actually store, that's actually held in the user service. So I'm going to go and ask the user service for some more pieces of information about you. And I'm going to put that on the web page, right? And so the music web shop goes to the user service and says, can I have Bob's details? I really, really want Bob's details. And the user service says, well, you know what? You're the music shop. I trust you. You're my friend. You've come to me with the appropriate certificate. You've been very conscientious. You've knocked on the front door. You've treated me well. So I trust you because you wouldn't ask me for things you shouldn't ask me for, would you? So we have a sort of, it's not an implicit trust, but once yes, the user service validates that the music web shop is who it says it is, I do like to anthropomorphize my services. It makes swearing at computers so much more therapeutic. At this point, the information about Bob is passed back from the user service to the music web shop, and it is rendered on the website, and the world is a happy place. Now, Bob, as we know from reading security papers, Bob is always up to no good. And so Bob thinks, I wonder what happens if I do this. So I go to my URL, and I take out the word Bob, and I put in the word Alice. So I'm logged in as Bob, but I'm now going to ask for Alice's information. Now, at this point, all the auth gateway is doing is saying, are you logged in? And you are logged in. The call goes to the music web shop. The music web shop says, can I have Alice's details? The user service goes, well, you're the music web shop. I trust you. And you wouldn't ask me for things that you shouldn't be asking me for, would you? You wouldn't do that to me. And so the information passes back, and Alice's details are now in Bob's hands. So that's not good. Now, this is actually an example of what's called in security engineering the confused deputy problem. Believe me, it took me 2 years of searching for variations of confused cowboy to find this picture. This is the best I could come up with. So the problem is, we've basically, a confused deputy problem is one where you trick an intermediary party into asking for things they shouldn't actually be asking for. You've gone to them and said, yeah, it'd be fine. And that's what's happened. What we want to happen here is we need to apply some sort of authorization. We need to say, not only that Bob is who they say they are, but also validate what is Bob allowed to actually do. The question is, where do we authorize? Now, some people like to authorize sort of up stack at the perimeter to stop the call even going through. But for me, this feels a bit odd. Fundamentally, with microservices, we're taking functionality and pushing it into other services. We're sort of distributing responsibility. And so the functionality that I'm trying to access is down here, but I'm expecting something upstream to understand what functionality will be needed as part of this call and make a judgment call at the perimeter about what they're allowed to do. So I'm never quite sure how that's supposed to work. Some of the schemes I've looked at involve some kind of centralized authorization service where every call has an additional round-trip check to say, can I do this, can I do this, which adds huge amounts of latency. I think it'd be much more natural if we can find a way, rather than making decisions upstream about functionalities downstream, instead actually have the services that have the functionality, give them enough information so they can decide locally whether or not this is something that should be allowed. The problem is we don't have the ability to pass the context of the call down to this user unless you put it into our protocol. So I've done a bunch of things to get this to work. So basically, the idea is we're going to try and take the context of the initiating user call and pass that downstream to a service to make the local decisions. I've done this before with nested SAML assertions. The one thing I should say about SAML is the one thing we don't need more of is more of SAML. So whatever you do, do not nest SAML. It is theoretically possible. You will definitely hate it by the end of it. So there are better techniques out there now. Instead, what we're going to do is what we want is this. We want Alice to come back and say no when Bob asks for Alice's information. This will not stand. So JWT tokens is probably the most popular way of solving this problem nowadays. A JWT token is a very simple idea. It is a JSON structure which allows you to put arbitrary JSON data. You then calculate a hash of that data. So then you pass the hash along with the data to downstream services. Those downstream services are able to validate whether or not that hash is valid, and therefore the data is valid completely out of band. Basically, you just communicate the keys via back channels. What that allows you to do is validate that these tokens are correct without additional round trips, and that's key for reducing latency in distributed systems. So here's an example, and here's an example hash. And so if I get hold of that token and I change the data to say I'm not Alice, I'm actually Bob, this will no longer validate. Again, you need to validate the hashes, otherwise what are you doing? So in this situation here, I'm logged in, I've got some kind of OAuth token or maybe a cookie-based token, and the auth gateway says, okay, well I know you're Bob, and so I'm going to let your call basically go downstream to the music web shop. And normally here, what people would do is they'd sort of exchange your OAuth token or your logged in cookie state for a JWT token. This allows you to put more information in the JWT token that is only communicated within your perimeter, and so you're not worried about information in that JWT token being made available publicly. So and in this situation, it's a very, very simple token. It just says the user is Bob. When we pass that token downstream, it goes along maybe in a request header, or if you're sending a message, you'd send it in as part of the message payload. That token goes downstream. The music web shop goes to the user service and says, can I have Alice's details? The first thing that's happened is at the transport level, we've authenticated that, yes, this is the music web shop that's calling us. We know that it's a request from a trusted service, but is the trusted service asking me the things it should be asking me for based on who the client is. And this information, the logic in the user service says, I will provide user details for users I'll only provide the user details for somebody that's the same user as the person whose data I'm asking for, if that makes sense. So Bob is not allowed Alice's details. Alice can ask Alice's details. And so in this situation, the user service goes, well, I've looked at your JWT token. You seem to be Bob. And based on my logic, that is not allowed. And therefore, no, you cannot use that. And so you'd pass back an unauthorized exception here. Now, of course, with a JSON token, like this is just a JSON structure, you could put more information in here. You could put a group. The group could be admin. And then maybe the logic of the user service says, I'll only give user data back to that user unless the user is also in the admin group, and in which case any admin can see that data. There are limits to how much stuff you want to put in these JWT tokens because they're effectively going to increase the size of each payload. I spoke to a client that was working in the area of digital rights management for music, and we did a quick back-of-the-envelope calculation on how big his JWT tokens would need to be to capture all of the kinds of information they needed to make these decisions, and realized that most of their JWT tokens, that their JWT tokens could be sort of tens of thousands of lines long, based on how their current permissioning system works. In that situation, what we decided to do was use very simple JWT tokens for the bulk of the flows, and then for the parts of the system where you needed more fine-grained information, you effectively then had to do additional round trips to some sort of credential store. So, very, very cool idea. Other things you can do is you can expire these tokens like you can with cookies. That causes some interesting problems if you're doing sort of asynchronous processing flows. So if an operation is going to take 5 days to complete, do I put a 5-day expiry on that JWT token? If I do, then the potential problem is that if that token is, someone gets access to that token, there's a bigger window where they could be misused. So a lot of people I know that do longer processing times sort of switch at a certain point to an implicit trust model built at a certain point in time. Another really exciting thing in the area of microservice and security spaces that can help us with some of these issues, can help with things like JWT tokens and certainly validating those tokens, and also doing other things like mutual TLS, are things called service meshes. And so probably two of the most well-known service meshes out there are Linkerd and Istio. Istio sort of is, I suppose, it's came from Google. It's the sort of de facto incumbent service mesh in a way for Kubernetes. But Linkerd has actually been around longer, and I certainly know more people running Linkerd in production. These models emerged to solve some really, really good, the model of these things is great, actually. The problems they're solving are real problems. When it comes to communication between services, there's a whole bunch of common concerns that we have. And those common concerns are things that typically we would solve by either expecting developers to code these things up from scratch or use some kind of library to implement these common concerns. And I mean here things like, okay, two services talking to each other, I have to worry about things like tracing, integration with Zipkin or Jaeger or whatever else. I've got load balancing and service discovery, especially if I'm doing client-side load balancing, which is quite common if you're using something like gRPC because of the multiplexing issues. Also, of course, authorization and authentication. Okay, it's more code that I've got to have on both client and server. And now maybe my connection resiliency and retry mechanisms. So am I using circuit breakers as a default approach? Don't know, don't care. But if I am, I've got to have that code everywhere, right? And so the common way to solve these common concerns is say we're going to adopt an open source framework. We're going to adopt something like Spring Boot, which is a perfectly fine choice if you're on the JVM. It's actually a very good framework for this sort of stuff. And that's great. So now we say all of our services are based on Spring Boot. That's fantastic. But then we have this other thing, right, where microservice architectures allow you to have different technologies in the mix. But what happens now if I've got some services running on Java, but I've got a different service running on .NET and another service running on JavaScript? It's a lifestyle choice, right? This is the things you want people to be able to pick the tools they're happiest with, right? But now suddenly all this useful code that you know works in the Java space, you've got to re-implement in the .NET space and re-implement again in the JavaScript space. Does it work in the same way? Is it consistent? Is it giving me the same kinds of experiences? And there's another problem as well here, which is even if you do adopt a framework and say everybody's got to use this framework for these common concerns, these common security concerns, you still have the version drift problem. The client is using version 1 of the framework, the server is using version 2 of the framework. You have potentially inconsistent behavior between the two, which I have seen cause issues. What happens when I need to roll out that change to that framework? Do I need everyone to have the same version available to you? Netflix dealt with this problem in an interesting way. They'd spent many thousands of developer hours into creating libraries that were the bedrock of how Netflix scaled and was made resilient. You can think of things like Eureka, Ribbon, Hystrix, and the like. And because of that, they basically said, if you're talking between two machines over a real network, you have to have the JVM on both sides. That's because we know you can therefore use our libraries that have predictable and understandable behavior, and we know they work. So you've got to talk JVM to JVM. The issue then became, well, what about non-JVM-based languages? What if I want to write something in Node? How do I play in this world? Are you saying that Netflix is a no-Node shop? So they said, well, actually, no, we can solve that for you too. So what they did was they adopted what they called at the time the sidecar pattern. So in this, you would write your service in whatever language you wanted, Node.js, Python, Ruby, it doesn't actually matter. It would then communicate with a local JVM process. So at this point, it is not a distributed system. We would communicate with a local JVM process, and that local JVM process has all of that shared and common connection-oriented stuff inside it. And so that any communication went over a real network. So you had the guarantee of JVM to JVM. You had all that common code between it. And so this is really useful. So effectively, this is giving you code reuse across application stacks. And the impact of version drift here is much more easy to mitigate. It's easier to roll out updates to these things. So in this sort of model, this led to you'd run one proxy per machine, and any services that were running on that same virtual machine would communicate via that proxy. And that proxy would then route traffic to other services. This gives you a centralized place to do common connection-related concerns. This is now sort of what's called the proxy model. There's a bit of a confusion around the language here. And a service mesh is basically something that sits on top of these proxies and gives you a control plane, a way to understand what these proxies are doing and configure and change their behavior. Now, the deployment models have changed somewhat. This is what Linkerd version 1 looks like in some of the early service meshes. These models actually also have a lot of flexibility about deployment models. These types of service meshes you can deploy on any kind of architecture, whereas some of the more modern service meshes really assume you're deploying onto Kubernetes, which I think is somewhat unfortunate. But anyway, so this is the shift in deployment model. So local proxy model was sort of where Linkerd version 1 is. The sidecar model is now what's called the sidecar model, which is a bit confusing because this was the original sidecar model, but terms get redefined all the time. It's more like this. So where Kubernetes allows you to schedule a pod, so that means you can have two processes, two separate containers deployed in the same unit of deployment. And so for every service instance you deploy, sort of sitting next to it on the same machine is your own instance of this sidecar process. And so you're looking here at things like Istio and what Conduit, as it was used to be called, is now called Linkerd version 2, which is incredibly confusing because Linkerd version 1 is totally different from Linkerd version 2. And so I now have all of these conversations with my clients about which one you're talking about. It becomes even more confusing if they say they're using Docker Swarm, because then it's either using Docker Swarm or Docker Swarm mode, which again are totally two entirely different tools. And it turns out marketing is hard. Anyway, this is the more modern model on the right-hand side. These proxies over here, to be efficient enough, tend to be written in things like Rust. So Conduit, Linkerd version 2 is written in Rust. The Istio proxies are making use of Envoy, which is written in C++. So very, very lightweight proxies. The benefit here is it makes it very easy for you to provide per-service-based configuration as part of your scheduling of this unit. Whereas here, this is a bit more of a centralized model. These things are often, certainly on Linkerd version 1, are JVM-based processes. They take up much more memory. You don't want loads of them between machines. So having this sort of common place in your fabric almost, Service Fabric is a better name. Unfortunately, Microsoft got there first and used it for something else. It's a great place to insert sort of common behavior and be able to control that across the whole piece. And it's really, really useful for all kinds of things. So it's really useful for things like load balancing, especially where you want to apply things like client-side load balancing or where you want to load balance over, say, HTTP2-based traffic. which has issues because of multiplexing. It also does some really cool stuff around traffic routing. It's aware of where things are deployed because of where it runs in the stack and how it runs, which means it can make sure it routes you to a service instance that might be local to the same machine as you. It can also handle you can push some of your service discovery type mechanisms into that space. You can also use it as a place of getting basic tracing. Although if you really want the detail that you want out of things like Jaeger, where you want deeper introspection of your service stacks, you're still going to need to instrument your code. But for things like correlation IDs, it's really great. And when it comes to security, you can use it to implement things like mutual TLS on your behalf. This is still sort of, should be there mostly, but they're renaming a bunch of stuff in this space for Istio, for example. But the idea is your mesh should actually be able to handle all the mutual TLS on your behalf. So now your service, I don't even have to worry about it. I know when I get deployed, I'm going to be deployed in an environment where the mesh is handling mutual TLS, JWT, and the rest for me. Kinda, right? Because I will say that there are a few spaces in the world of Kubernetes and containerization that's having more churn than there is service meshes. There's a new service mesh being released every week, it seems, and lots of the people who create API gateways are now saying, oh, no, we're a service mesh, which is confusing things even more. I mean, it's just on the hour, which means another VC would have popped about 20 million in someone's pocket to build another service mesh. And so this is a bit of a churny space. If you had to pick one, Istio seems like a pretty good bet, but I know loads of people that really love Linkerd version 1. I think as long as you're prepared for the fact that the decision you might make today might shift tomorrow, that's okay. Anyway, we're a bit over time. Just some basic summaries, patching and passwords, patch your stuff, change your passwords when appropriate. Think about how you store secrets, use things like Vault. Worry about transport security once you've dealt with the basics. Like if you're not patching and your things, and transport security is lower down your list of worries. Authorization, think about authorization of human beings. And finally, consider service meshes. That may be something that's useful to you. I have a bunch more information over on my website. I've got a whole 3-hour course on microservice security that you can watch as part of a free 30-day Safari trial. But you know, pay some money, I've got to buy a house. And so you can find information on my website. And thank you very much indeed for your time.